In one of the previous lectures, we discussed the interference of light. In particular, we discussed the interference between two sources of light that you either get if you split the phase front of an incident beam, as you do in Young's double slit, or that you get if you split the amplitude of an incident beam, as you get in thin film interference, where you get the reflection from the top surface, from the bottom surface, and these two contributions interfere. In this lecture, we'll discuss the interference between more than two sources of light. In a similar way, we either split the amplitude of an incident beam, the phase of an incident beam, or the amplitude of an incident beam. Here on the top, we have interference behind N slits. And here in the bottom, we have interference between N beams that you get from multiple reflections in a film, either in reflection or in transmission, because of course also in transmission do you have N beams, N beam interference. Why would you be interested in the interference between N bigger than 2 sources of light? The key word is interferometry. Interferometry is the use of optical interference to analyze light, and in particular to look at the optical spectrum of light, to see what colors are inside the optical source. This is an example you've seen before. It shows the interference pattern behind Young's double slit when you illuminate it, for instance, with light that contains 2 colors. The interference pattern behind Young's double slit, so the intensity as a function of angle, for each of these colors is a cosine type pattern. But if you have 2 colors of light, you have 2 different cosine patterns with a slightly different period. And as a result, the total interference will exhibit a beat. And if you see these oscillations with a beat, you can deduce that the light contained 2 colors. Now, if you have a source, white light-like source with multiple colors, with a whole spectrum of light, then what you typically see is in the center of the interference pattern at theta is 0, you see all colors constructively interfere. So you see white light, just as the source is white. But if you go to different angles, you see that the different colors exhibit a different interference pattern. So you see a separation of the colors. And you understand that by looking at this separation, you can deduce information about the optical source, and in particular, its optical spectrum. Now, if you look at the intensity behind 2 slits, the intensity pattern of each of the contributing colors is a cosine type function. So a pretty smooth function, which makes it rather tough to distinguish one color from another color with a slightly different wavelength, just because these cosine functions exhibit too much overlap. On the other hand, if you look at the interference behind 8 slits or 16 slits, then these interference patterns become much sharper. And hence, if you now try to separate 2 different colors, then periods are different and it's easier to separate colors. And it becomes even easier, becomes easier if you have more slits. And it also becomes easier if you look at the diffraction in higher order diffraction maxima. So this is the first order, this is the second order, etc. And you see that this spacing increases the higher the order. So what does this slide show you more? It shows you the functional dependence of the intensity as a function of angle for interference behind N slits. It shows you the crucial parameter that determines the interference, which is a phase difference related to a path length difference divided by lambda, more to follow. And it shows you the spectral resolution that you get in the interference pattern behind end slits. A spectral resolution that is defined as the ratio between the wavelengths of light and the wavelength difference that you can observe if you look at this interference pattern. And that spectral resolution is proportional to the number of slits, right? I mean, if you have more slits, it's easier to separate two neighboring colors, but it's also proportional to the order of the diffraction. If you're in second order diffraction or even third order diffraction, the spacing between these peaks increases and it's easier to separate them. The spectral resolution increases. Let's do some math to describe the interference between light emitted by n sources. So we consider n sources illuminated from this side, emitting under a certain angle, theta, and we discuss the interference between this light and this light, and of course the crucial component to describe this interference is the phase difference, phi, between light from consecutive sources, and that phase difference is 2 pi times the length difference divided by lambda, where the length difference here is this additional distance that one of the sources of light has to travel with respect to the other source of light, and that length difference is d times the sine of theta, because theta, the angle with respect to the surface normal, is also here. So this is the crucial component in the derivation. How does the derivation continue? We look at the total field emitted as a function of angle. It's this contribution, which we can call 1, and then this one, and this one, and this one, and the consecutive contributions are shifted in phase by this phi. So if you call this one 1, then this is e to the power I phi, this is e to the power 2 I phi, etc. So you have to solve this sum. So let's continue with the derivation of the math. We were discussing the sum of various contributions, or contribution from various slits. For instance, in this form, 1 e to the power I phi, etc. In this expression, very similar, but here we take as a reference, as the origin, the center between these end slits, in such a way that the contributions from slits below this origin have a minus sign, and the contributions from slits above the origin have a plus sign. But even then, you can factorize out the phase of the lower slit, again get this sum, and rewrite it in this form and in this form. So the crucial step here is this sum, which you can also write as this sum if you interpret this x as the exponent I phi. So how do you solve this sum? Let me show you the trick. The trick is that you multiply this sum by x. And if you do that, then the first term, this 1, becomes an x. The second term, this x, becomes x squared. The third term becomes x to the third, etc. up to this point, and the final becomes x to the n. And now the trick is that you write these two below each other and subtract. And then if you subtract this guy from that guy, you get on the left side of the equal sign 1 minus x times this. On the right side of the equal sign, you have a 1 from this one. Then x minus x cancel, x squared minus x squared cancel, etc. This one cancels against that, and you are left with this term. So eventually you see this is equal, the sum is equal to this expression. This expression. Cute, isn't it? There is a small catch in the previous derivation of interference behind n slits, and that is that in the previous derivation we assumed that each of these slits of the n slits was very small, and that if you illuminate it with a plane wave, it emits an equal amount of light basically in all directions. Now, if you have slits of a finite size, here described as wider slits, upon illumination each of these slits emits a diffraction type pattern which might have lots of intensity in the forward direction, but maybe much less in particular angle, at particular angles. And of course, if each of the individual slits has a diffraction pattern and hardly emits light in a particular direction, then if you have n of these slits that interfere, the interference pattern of n of these slits, which for very narrow slits is an equidistant series of peaks, will not be a series of peaks of equal strengths, but you have to multiply the interference pattern of n delta-like slits with the diffraction pattern of each of the individual slits, here in red, to get a total diffraction pattern, which still is a series of interference maxima, but now multiplied by intensities given by the diffraction pattern of each of the individual slits, here in red. This slide is a follow-up of the discussion that the shape of each of the individual elements of n slits, or n elements in a grating, determines the intensity pattern upon reflection, for instance, from this grating. If you have very narrow emitting elements, these will emit equal amounts of light in all directions, and you'll get a series of equally bright diffraction orders. If, on the other hand, you have highly structured patterns, like in this case a Blase grading, what you get is that the diffraction from this grating, here 0th order diffraction with theta out is theta in, you get a couple of diffraction orders, and by playing with the shape of this grating you can modify the intensity of these diffraction orders. This is a very particular case, a so-called Blase grading, where each of the elements is like act like a mirror. You have a sawtooth type structure of a reflecting mirror, and with sawtooth you understand that if you think in terms of ray optics, most of the light will be specularly reflected. So with that in mind, you can understand that in this case the strongest order will be approximately MS3, because this MS3 is close to the angle of specular reflection. So by playing with the shape of the elements, the n elements of a grating, you can modify the intensity distribution over the diffraction orders, and a particular cute modification is a so-called Blase grading, sawtooth-like grating, where you can get a lot of light in one of the particular orders. This slide illustrates the argument that the pattern you observe behind n elements, n slits, is the product of the diffraction pattern from a single slit multiplied by the interference pattern behind n point-like slits. In equation form, the emitted field as a function of angle is the product of this sink-type diffraction pattern of an individual slit multiplied by this pattern that you get for interference behind end slits. So let me walk you through the figure. The first picture here is for a single slit, the diffraction pattern for a single slit, where the central maxima is of course at theta is 0, and where these minima and the next minima are related to zeros of this sinc function. Just diffraction pattern of a single slit. Now if you have two of these slits at a certain distance, what you'll get is you'll get a pattern which still has these zeros, because each of the individual elements doesn't emit light in a particular direction, so why would the double slit do so? But this diffraction pattern of a single slit is multiplied by a cosine type pattern related to the interference between two point-like sources or slit-like sources. So you get a cosine type pattern which has maximum here, 0 there, maximum here, 0 there, etc. Now if you increase the number of slits, what you notice is that the positions, angular positions of these maxima, they stay intact, but the maxima become sharper, and in between the maxima you get a couple of side maxima and minima. Here only, for NS3 only 1 additional, for NS4 2 additional, etc. Right. So you see the peaks sharpen up. They are still at the same angles, but they sharpen up for more slits. Up to now, we considered the interference pattern behind an end slit illuminated at normal incidence, where the interference criteria, or the criteria for constructive interference, was related to a path length difference between two contributions, which translates into the equation path length difference d times sine theta is a multiple of lambda for constructive interference. Now you might wonder what happens if I illuminate this end slit at a certain angle. I hope it doesn't take much imagination to understand that if you go straight through, you still have constructive interference. And effectively, the whole interference pattern behind the end slit rotates a tiny bit if you illuminate the system away from normal incidence. So if you want to catch that in an equation, you now have d times sine theta in minus d times sine theta out is m times lambda. Or written in a different way, d times the y component of the incident wave vector kn and the y component of the output wave vector ky out. That difference multiplied by d is a multiple of 2 pi. We've seen this slide before. In the previous slides, we discussed the interference between sources of light that you get when you split an incident wavefront, either in two sources of light or, more general, in n sources of light. Next, we will consider what happens if you split the amplitude of the incident light. You know this case, thin film interference, reflection from the top, reflection from the bottom, two sources of light. We will now consider the interference between n sources of light that you get if you consider multiple reflections in a thicker film typically, which reflects a lot, just because you have mirrors here, for instance, on the thicker film, or interference between multiple transmitted beams. This slide shows what happens in this multiple interference. So we consider an incident beam of light, incident on a certain slab of material, which typically reflects a lot on both sides. And to do that, what you often do is you add a mirror coating to this slab in such a way that the reflection becomes close to 100%, which means that if you want to describe interference of light in this system, you typically consider reflection, the first reflection, but you also have a second reflection, you have a third reflection, etc. And there is a long series which slowly decrease in amplitude. So to calculate what precisely happens, you have to trace the light and see what happens to this light. So let's look at transmission specifically. We consider an incident field strength E0, field amplitude E0, and the first transmitted beam you get when you have transmission through the top surface, transmission amplitude T, transmission to the bottom surface, transmission amplitude T prime, and on top of that there is also a phase factor related to half a round trip. And the crucial parameter to describe this type of interference is indeed the phase that you acquire upon a full round trip. And that phase is some sort of path length difference divided by lambda multiplied by 2 pi, the usual thing, where in the path length difference you recognize 2d, d being the thickness of the film, you recognize the refractive index of the film and the cosine of some sort of internal angle here, often 1. Now, if you want to add all these contributions, what you do is you get a total field here, which is the first transmission, second transmission, third transmission, etc. And you again recognize this series 1 plus x squared plus etc. that we saw previously. So with the previous math in mind, the field, the total transmitted field, is equal to the incident field multiplied by 1 minus r divided by 1 minus r multiplied by this phase factor. This figure shows the transmission through a slab, vary Perot, as a function of the phase delay experienced upon multiple reflection. So it's basically a representation of the equation that I showed previously, this 1 minus r divided by 1 minus r times the exponent. And what you see a couple of things. You, for instance, see that the peak transmission here is 100%. Peak transmission that you get if this phase is a multiple of 2 pi. Obvious from the equation, but not so obvious if you think about it. That if you have close to 100% reflection here, close to 100% reflection here, that still, due to these multiple interference of the various contributions, that you get a max transmission of 100%. There's a separate web clip on that. So that's the first thing that you notice. The second, and maybe even more important thing to notice, is that if the reflection of each of these layers becomes large, then the interference is visible only if phi is very close to this multiple of 2 pi. So the interference, the transmission maxima, become really sharp. And the sharpness you express in terms of the finesse is the period between consecutive peaks divided by the width of consecutive peaks. You could also say it's the average number of reflections that you have in this slab before the intensity decays by 1 over E or something like that. So again, you hopefully understand that you can use this interference in the slab for interferometry to distinguish different wavelengths, just because if you have a different wavelengths, you probably get a similar pattern but then shift it with respect to the original pattern. So you can use this to distinguish different colors of light. Again, you can define a spectral resolution in the usual way, and this spectral resolution is related to the ratio between the path length, the optical path length of this multiple reflected beam divided by lambda. You can also express it in terms of the order, which is, say, 2 times the thickness of the slab refractive index cosine theta, if you want to be complete. This thing multiplied by the finesse, which is the average number of bounces that you get, approximately. To finish off, a discussion on a related device, a Michelson interferometer. You've seen it before, a mirror that reflects typically half of the light, transmits half of the light in this configuration. So what you get, the instant light splits, you get interference between this light and this light. And the intensity that you measure here depends on the path length difference between the 2 arms of the interferometer. And this interference that you get by splitting the amplitude of the incident light, of course, looks a lot like the interference in a thin film that you get by splitting the amplitude of the incident light in the first reflection and the second reflection. But in this case, with the Michelson interferometer, you're able to tune the path length difference just by moving this mirror, whereas here you would have to tune the thickness of the film, for instance by using a wedge. So what can you do with this Michelson interferometer, with this interference between the 2 different contributions? Well, what you typically do is you measure the intensity of this interference light as a function of the path length difference, the length difference between the 2 passes, and then from that try to deduce information on the light, interferometry. So let me give you 2 examples. One is, suppose the incident light has 2 colors. Then each of these colors interferes with itself and produces a cosine type oscillation pattern. But if you have 2 colors, you get 2 different cosine type interference patterns, and you get the bead that you've seen before for a bead behind Young's double slit, if you illuminate Young's double slit with 2 colors of light. So when you see a bead behind Michelson interferometer, you deduce, okay, apparently 2 colors. Typically, if you have many colors, you don't see a bead, but you see something like oscillations with a certain envelope, and this envelope is related to the spectral width of the source. So again, as usual in interferometry, you might wonder how powerful is this device? How well is it suited to separate different colors of light from each other? What is the spectral resolution of the Michelson interferometer? And that is related to the path length difference that you can reach in the Michelson interferometer divided by the wavelengths of light. So to summarize and wrap it all up, this lecture considered interference of light, and in particular going from 2 sources of light to n sources of light. We distinguished 2 types of devices for that, either devices that split the phase front of the incident light, as you have in Young's double slit, and for that we extended it to something that we call the grading. So n slits, either like you do here in transmission, or some grating structure that you observe in reflection. So that's one type of devices. And the other type of devices that we considered was devices where you split the amplitude of the incident light. The simple case, interference from a thin film, where you consider the interference between reflection from the top and from the bottom. The more complicated film case, where you consider the interference in a film that reflects, where each of these surfaces reflect a lot. And if that's the case, you have to consider interference between multiple sources, between n sources, and going to infinity with decreasing intensity. And that thing is called a Michelson interferometer, and I made a separate clip for that thing. For this thing, finally, the thin film interference, there was also a different form of interference that you get in a Michelson interferometer, and by observing that interference as a function of the delay in the interferometer, you could deduce the full optical spectrum Fourier analysis. Thank you for your attention.